Hello everyone. So today we will start digital signal processing. I hope. Yeah. So I think Raja has joined. I am waiting for some more students to join. So just give me 2 minutes. I will start the class. So basically, week 8 was about predictive coding. And there we had what is the difference between correlation and convolution. So here in predictive coding, what is a basic thing? Like in correlation, the pixels are compared with each other with respect to one reference. Whereas in predictive coding, you'll have the current pixel is similar to the previous pixel. You will have the differential coding where dxy is equals to ixy minus ix1 x minus 1 into y. So this is what it is showing is differential. We have to check with the differential value and this dxy prediction error which is yet to be encoded. Okay, so we will be seeing this with respect to MATLAB in MATLAB online platform. So yeah, so I just want to give you some intuition. Then we will go to MATLAB and we'll see signal processing and the communication perspective of it. So if you want to see the predictive coding in the terms of block diagram, so here you will have the input image and at the end you will we are getting the compressed image. So what this predictor does is like it will predict some f of n where f of cap of n where it will have this summation of plus minus and where it will have en and then finally the symbol encoder and it will give the compressed image. Okay, so at the time of decompression, what you will do is the input you will have the compressed image, then you will pass it to a symbol in decoder, then you will just pass it to the summation plus minus, and again you will have the predictor, and en will be multiplied with f of n. So this is how the decompressed image you will get that. Okay, so if you want to see the image, so we can have this A, B, C, D. So distribution for the original versus derivative images, this is A and B are the original and the gray level image. So how you might wonder like how we are converting this image to a grayscale image. Okay. How we are converting this, each pixel have the value from 0 to 255. Okay. So here we are converting. There are some people in the lobby. I'll just try to add them. Just give me a second. Manisha wants to join. Okay, I have let her it. Manisha, Parul, give me a second. I'm just letting them to join. Okay, Manisha, you are admitted. I have added you also, Parul. So we have Manisha, Parul, Raja, and Amber. Okay, fine. I am not sure whether my voice is visible or not. Okay, so this is what like we are converting the even image to a grayscale image form because we have each pixel as a value from 0 to 255. And then finally, the histogram for the original and derivative images can be found as a C and D. So this E of n square is nothing but expected value of Fn minus summation of alpha L Fn minus 1 whole square, where R inverse is the inverse of the M cross M autocorrelation matrix. So here we are just doing it in the form of Fn minus 1, Fn minus 1, and Fn minus 1 and Fn minus 2. Similarly, Fn minus M, Fn minus M. Okay, this is what the autocorrelation function, which is the form of PSD matrix. Okay. Now, suppose we have this X cap. So X cap can be calculated as A cap. Okay. Where we have this 91, 99, 96 as a plus reward plus 8, 4, 103 as plus 2, 104 as plus 1. This is what about the predictive coding. Now, in image compression, we have two type of compression. That is, first one is lossy compression, where we will have some redundancy, where it will keep some more important information, and it will have the trade-off between loss and the compression. So here we can see the original image. We have this one. Okay. Now the compression ratio is 7.7. Okay. In the second image, is the compression ratio is 12.3. So you can see the degrading value. Okay. As the compression ratio is increasing, so you'll have the more degraded image. But sometimes we don't even require to have more quality value. That is not at all required because we want better. Okay, not best. So this is what about lossy compression. Okay. Now we have quantization. This, as we know about when we convert analog signal to digital signal, then we will have that first thing is a sample. Okay, first we will take the sample, then we will quantize. Quantize means approximate. Okay, then we finally encode to some levels. That is the way that we do. So basic thing is first we have to discrete value to present the range of values, which is irreversible operation, and that will cause some information loss. So here you will have some information loss, and we will have the loss of and the possible occurrence of the errors. Okay, so here we will have the predictive coding and the transform coding. So you might wonder, the predictive coding is one type of transform coding. Okay, so here we can see the compression and decompression, as we know already, which is a lossless, not is a lossy, because if we do the lossy, we will have some trade-off. Okay, with that trade-off we will do. And if we have the lossy compression, so you can see the difference. Okay, lossless. This is lossless. We are not doing any loss. Okay, this is not having any loss. So it is lossless. Where when we have the lossy, then we will have this predictor, and this is summation plus one, and this is f dot, and this is en plus f power n. Okay, where we will have this predictor, but in decompression we don't have any difference. Okay, so we gradually, sir also shifted from this predictive coding to the digital communication. So here we can see this. This is the delta modulation where this f power f cap n is alpha f n minus 1, and en is equals to plus delta if en is this will having the threshold value particular greater than 0, or minus theta if it is less than 0. So this is what we actually do in delta modulation. So what is modulation basically? So Raja, you were there in the last class. Can you please tell me what is it modulation? Manisha, what about you? We already saw in the last class uh, through the simulation as well. Yeah. So, Manisha, you were telling something. Manisha, please don't. If you have any issue, please call me. Please raise your hand. Yeah, we will be seeing the simulations through online platform. We will come in 10 minutes. Just give me a 10 minutes. So I was telling about the quantization. Okay. So how the predictive coding leads to this quantization, then delta modulation. Okay. You can see this and visualize. And after that, we finally reach to digital communication. Okay. No connection. Okay. So Deshant also joined. So basically, after this predictive coding, we can actually approximate with respect to delta modulation. Then finally, we have this lossy compression. So as we know, we need to change this analog signal to digital signal, and then we will do this quantization. So here we will have this input. Suppose we have this input 0, 1, 2, 3. This f as these values. This is the f function. This f cap is the predictive value. The error calculated, this is the f cap minus f. Okay, this is e dot that we had. Okay, and this is what this delta modulation that we approximated. Okay. Then finally, we have this granular noise, okay, and the slope overload. So slope overload means d by dt of mt is greater than delta size, okay, delta v by delta t. So this is how this slope overload, and in the reverse case is a granular noise. So you want the perfect approximated function. So you don't want either granular noise, neither slope overload. So this is all about this lossy compression. And if we have the uniform quantization, so what does this mean? Name suggest this uniform quantization in the sense that the step size will be same across all the levels. So here you can see if you have this uniform quantization, the step size, this is this step size. Okay, this is same. And how this uniform quantization and difference image leads to this particular value? This the 204, 102, then 0, then minus 102, then minus 204, because you had this value, okay? Then after subtracting this delta, you will have this value. Then after subtracting this delta, you will have this value. Then you have subtracting this delta, you will have this value. Similarly like this. But you have suppose one level this and one level this. So this will goes from here to here. Why minus 255 to 255 we are taking? Because pixel values ranges from that. Okay. So this is all about the lossy predictive model. Okay. I will just go to other topic which was covered in the class. I will go into deep about this transform coding. Okay. So this under this transform coding, you have this predictive coding, okay, which is a technique. Okay, it is a spatial domain technique since it operates on the pixel values directly. Okay, transform coding operate on a reversible linear transform coefficients of the image, which is that is also called DCT, DFT, or Walsh. Suppose you have this input image cross n, which will construct this n cross small n cross n sub images. It will forward the transform. Then it will have the quantizer, and finally there's a simple encoder, and finally you will have the compressed image. This we already saw in the form of circuit diagram or the flow chart. Okay. But if we want to see in the blocks, so this is all about the blocks. When we want to have the decompressed image, or if we have suppose input as a compressed image. So compressed image is the input, and the symbol decoder is the output. It is passed to a symbol decoder. Then inverse transform. The transform means what? Can anyone tell me what is? Can anyone tell me what is transform here?
Ma'am,
Yeah, yeah, sure. Amber, tell.
ma'am, DFT.
Yes, very true. So here we are talking about DFT because uh, uh, because we want to do the transform. Transform means nothing but the time domain signals are transformed to a frequency domain signals. And if we talk about discrete time signals, so the discrete time signals will be passed to a DFT. Okay, not even DTFT because DTFT you will have the input as a continuous time signals. That is not a answer. Okay, DFT is a correct answer. Very true. So at the end, the quantizer selectively eliminates or coarsely quantize the coefficients with least information, whereas the symbol encoder uses a variable length code to encode the quantized coefficients. So any of the steps above can be adapted to sub-image because the one image will be split into various sub-image of different sizes based on the local information or the fixed or the sub-image. Now this Walsh transform, which is a particular case of 1D case. Okay. So when we have this one-dimensional image sequence, the one-dimensional image means it's just a sequence where it will have f of m is equals to 0, 1 to n minus 1. Okay, where n is equals to 2 power q. The q can be any value where the power should exist. Its Walsh transform, which is w small q, can be defined as like this. So what does this mean? So we are multiplying the each coefficient of this f of m. Okay, we are multiplying the each coefficient of s of m where it will go and it will sum. So what does it mean? So first of all, it will multiply with all the minus 1 q minus 1 because we have this n is equals to 2 power q. Yeah, so it will go from 2 to q minus 1 since it is discrete, so it will start from 0. Okay, then based on all either even or odd, okay, it will multiply and it will finally sum into every f of m. Okay, where b of kz is equals a kth bit from LSB, the binary representation of z. Okay, I think that was not covered in the class, so I think I can skip this. But yeah, if anyone wants to, I will share this lecture in the PMRF NPTEL portal, so you can have this homework problem as well. But it was not at all covered in the class, so I'm just leaving as of now. So I'll just share my screen to show this MATLAB coding. So last time we saw what is how to generate the digital signals and then also resampling and modulation. This time I'm starting with again this signal generation and resampling. So basically, what I am teaching is through signal processing with MATLAB because this is all about, you can see this power spectral density, which was covered in week 6, and how to calculate this discrete Fourier transforms in zero padding windowing, and finally how to characterize the digital filters. So I'll cover some part, okay? Wait, let's share the screen. What happened? I have to share the sound as well. Stop sharing. Include sound. So what we are having the real world signals, it's not feasible to acquire all the signals. So how to manipulate, how to do all the operation with the signal, that is a main task for us. So engineers generate the precise signal that will mimic the real flight scenarios to simulate and predict. So here the concept of modulation comes into the picture because in signal generation, we are having the space, amplitude, and frequency. That's why the modulation is the process of varying the modulated signal, the message signal in accordance to the carrier signal. The carrier signal will have the space, amplitude, and frequency. So these parameters of the carrier signal will be varied, okay, in accordance to the message signal. So that's why we always change these parameters, and the parameters of these carrier waves are often better in terms of the actual message signal. So the frequency, suppose if we say frequency, the carrier wave frequency is much higher than the message signal frequency so that we can have the higher frequency modulated signal. Okay. But in MATLAB, we have the easily generating functions. Okay. Like we can have sine, chirp signals. But the question arises, how can we decide which type of signal to generate or what parameters to use? But at the same time, if we have different mobile phones, let it be Apple, let it be Samsung or any other company. So it will have the different vibration inputs, okay, because different systems respond to different inputs. So similarly, the communication system, for instance, will also have different types of inputs and different types of outputs. So basically, it will lead the modulated signals, whereas an audio system may not need the modulated symbol. Okay, modulated signal. So we have two different systems where we have this communication system as a mobile phone, and the other one is the audio system. So in audio system, you will have uh, the capability of modulated symbol. So range of frequency will be required by audio system, whereas the different signals will be required, or the modulated high frequency modulated signal will be required for the communication system. So it is actually not just about creating a waveform. You have to optimize the parameters that tune the signal. So what are the parameters that we saw? The amplitude, phase, and the frequency. It's about understanding the environment in which system operates. So, what is sampling rate? Like the rate at which the samples will be taken from a waveform. Okay, that is called the sampling rate. Sometimes in some signal we require more samples to represent that signal, whereas in some other case we'll require some less number of samples to represent the signal. Okay. Sorry.
Well, let's get started. Enjoy the course.
So I was just telling like in between the screen share stop. So what I was telling is like we can have the different type of signals and the signal generation. So we will see how to generate the signals so that you will have this understanding and what type of signals will be required. So in this particular session, we will have the understanding of generation of different types of signals by setting different signal parameters, choosing the correct sample rate, adhering to sampling theorem for a discrete signal, and generate this discrete signal by sampling an analog signal and apply the resampling techniques to adjust the sample rate of a signal without introducing the distorts. Okay, let's go ahead. Okay, for example, you have this you have probably seen this digital watermarks on the images. But did you know that you can also watermark the audio files? The watermarks can be used to identify and verify the owner of image. Okay, this is very obvious. We will see then after that this one. So first task is if you want to you need to choose a sample times where the signal should get generated. So you can choose the sample times or specifying the sample rate, start time and end time. So suppose task one is FS is, what is FS? FS is 100 hertz. Then we need to create T where it will range from 0 to 1 by Fs. And finally, we'll have this 3. Sorry, not hertz. Then we have to create a sine function and then we have to do the plot. Okay. So this signal is created and we have to plot it. Plot sig. So let's do that. So we can see the screen, but I think, okay, this is T, this is, because we have to specify this x-axis and the y-axis properly. To create a signal with the multiple tones, you can add the sine waves together. So we can add the another signal with tone at 3 hertz, at 3 hertz from the previous task and name the result to sig. So adding another signal with a tone at 3 hertz. So let's sig is equals to three hertz, okay? 3 hertz, okay? Plot B sig. So you can see this how the multi-tone differs. Oh, nice. So PS spectrum to view this signal. Let's see this power spectrum. So you can see this power spectrum. So here you will have the frequency of 854.7. Okay. Now we can see this, as I was telling, which parameters we have to change. So if we change this amplitude, okay. So how this amplitude is changing? Amplitude got changed. Suppose I want to change this F. So how the frequency is changing. So frequency is increasing, then this will be becoming more closer. Right. Now how the phase is changing. So phase 120 completely opposite. Okay. Now you can create your own audio mark and changing this particular thing. You can change something. So Now, the signal that you'll watermark in this module is a recording of a flute playing one note. Okay. You can import the audio files with the audio read, and then using the separate the variables of the signal data and the sample rate. So suppose, for example, if we want the signal, okay, this is having the size of 111118400 cross 5. This is the class of double. Okay. So how can we have this audio that is already imported to the workspace for you? So before you watermark the signal, you can visualize in this activity. So how can we visualize? Recall that we can visualize the signal by dragging on the workspace. So, okay, workspace we can drag and let's visualize this flute. Okay, these are the signals. I think it's okay. So this is like flute. This is a signal filter name, and this is FS. Okay, great. Okay, now the audio is already imported. Before you watermark, you can visualize. Recall that you can visualize the signal by dragging them. Okay, to set the time information, select the time values in the analyzer drop. Analyzer set time. Okay, select time. Time values and analyzer time. Where is it? Time. Okay. You can specify the sample rate. The sample rate was 100, I guess. Time values. Specify the sample rate and the sample time of the vector of time values. So, 60 kilohertz, right? You can see this. That sounds good. Okay. The end of the signal has a larger amplitude. Okay. That is having a larger amplitude sound. It makes it difficult to see the rest of the signal. You can extract the portions of the signal using this panel in the display tab. So, panel, where is the panel? Ensure the panel is set to the full length. It is a panel. Modify the flute signal so that it only contains the first 7 seconds. Zero. So here we don't have any option to put the end time, but you can extract the portions, the panel, using the panel in the display tab. The panel, I couldn't see this here. Display tab. Panel. Fingers. Oh. So basically, this is all about this display function. You will have this time spectrum spectrogram. I think this is all about this panel is to set the full length of the original signal. The full length. If any one of you can see this panel option, you can just let me know in the comment section because I can't see that. Okay. And if you want to go to the next one, it is all about that only. Play. If you want to play that, data cursor. Okay, that's great. Let me share this sound also to you. Okay.
Most real-world signals are continuous functions of time. You can get the value of the signal at any time you want. But to efficiently process signals on most computers, you need a discrete time signal. This means you only have data at specified times. To sample a continuous time signal, you need to choose a sample rate based on the frequencies that you expect. Different applications encounter different ranges of frequencies. Seismic activity is relatively slow. Most earthquakes will generate waves below 10 Hz.
So
Compare that
one
to
general
audio
knowledge,
signals.
most
A human
earthquake
ear
kits.
can hear sounds up to 20 kilo audio signals. A human ear can hear sounds up to 20 kilohertz. If you tried using the same sample rate for both applications, a rate that's reasonable for the audio signal would end up storing way too many samples of the seismic signal, resulting in higher computer memory usage and a slower computation time. On the other hand, what's reasonable for the seismic signal won't be enough samples to detect the frequency in the audio signal. So, how many samples are enough? Intuitively, you need to sample faster if your signal has higher frequencies, because your signal is changing faster. For a real continuous time signal, the spectrum has content at your signal's frequency and the negative of that frequency. To get a discrete time signal, you need to sample the continuous time signal at a regular interval, determined by your sample rate. Once you have enough samples, you can use FFT to estimate the spectrum.
So we can
The
use FFT to estimate the function.
resulting discrete time signal has replicas spaced by your sample rate, and there are infinite positive and negative replicas. Well, this is a pretty simple signal. It has just one tone, so it's easy to distinguish between the original spectrum and the replicas. Most real-world signals aren't just one tone. There's frequency content up to some maximum frequency. In the discrete time spectrum, all these frequencies are replicated. Remember that the replicas are spaced by your sample rate. To keep your original frequency content untouched, your sample rate needs to be greater than twice the highest frequency in your signal. This is sometimes called the Nyquist rate. If you use a sample
I hope you want this Nyquist rate. Nyquist rate is nothing but Fs by 2
rate that's smaller than the Nyquist rate,
because that will be the end point to have the Nyquist criteria where Fs, the sampling rate should be greater than or equals to the twice of F max. Why twice of F max? Because you will have this two types of distortion. First one is the aliasing, and the second one is the wastage of the bandwidth. So if the aliasing happens, you will have the loss of information.
the replicas start to overlap. You might expect only the higher frequencies in your data to disappear. But when this information is lost, you have interfering power at lower frequencies too, called aliasing. Aliasing occurs when a signal is sampled in a way that makes it indistinguishable from another signal. Remember that your goal is to accurately represent a continuous time signal with discrete points. In order to get your original signal back, just remember to choose a sample rate that's greater than twice your highest frequency.
So here we were having signals in real world are either analog or the continuous time. So, but in computing, most signals are digital or the discrete time. So, how does this affect our signal processing? Okay. So, for real valued signal, the magnitude spectrum is symmetric around 0 hertz. Now, as we saw in the video, you introduce the repetitions in the frequency domain when we sample the signal in the time domain. So what is happening here? We are sampling the signal in the time domain and you're getting the repetitions of frequency domain, and every repetition is governed by the frequency, which is Fs. In general, you want to keep the frequency at the same location in analog and digital signal, but this Fs is what we need to choose. So we need to choose our sample rate so that the repetitions don't overlap with the original spectrum. So our sample rate should be at least 2 of F max. So I hope I told you this. Again, this is all about the spectrum. So I think I can move to time frequency analysis. I'll just continue this one. So, okay.
Imagine observing signals from two different seismic stations. From the first station, the signal appears consistent, almost uniform in frequency content over time. From the other station, the signal has different frequencies at different times.
So this is what
Frequency
about this
analysis
time
methods, such as
frequency
the power
analysis.
spectrum, would provide a snapshot of the overall frequency content of the signals. However, the second
This is what the snapshot of the overall power content is nothing but the power spectral density. And we already saw about this power spectral density in the previous classes, so I'm just ignoring that.
seismic signal is highly dynamic, with varying frequencies and amplitudes over time. So with simple power spectrum analysis, you lose the time information.
With the simple power spectral information, how you are losing the time information? Because it is not at all covering this time perspective of that signal. So here, the amplitude is varying with respect to time, but with the power spectrum analysis, you can also only see uh, the center frequency and the analysis of the power with respect to frequency.
Time frequency analysis allows you to visualize
Whereas time frequency analysis allows us to visualize how different frequency components emerge and how they uh, distribute and how they accomplish.
Realize how different frequency components emerge and evolve over time.
Basically, evolving of signal over time.
This enables you to identify specific events, such as earthquakes or ground vibrations,
So this enables us to find the specific information like the earthquake or extract the valuable information or the about the
and
characteristics.
extract valuable information about their characteristics. Spectrogram and scalegram are two standard ways to do time frequency analysis. Both decompose the signals to a combination of simple functions, either sine waves or wavelets. The choice of technique depends on the scalegram are two standard ways to do time frequency analysis. Both decompose the signals to a combination of simple functions, either sine waves or wavelets. The choice of technique depends on the specific characteristics and objectives of the signal analysis task. As you progress through the course, you'll better understand both techniques for analyzing time-varying frequency signals. So let's get started. Enjoy the course.
So basically here we are here it is. So as we know, we already saw what is the power spectral analysis, and we also saw the simulation of power spectrum analysis. But for the time frequency analysis, that analysis doesn't cover the time varying nature of the signal. So that's why we saw this predictive coding, and then we went to this delta modulation and how this time frequency analysis of the signal is important. So we will learn how to estimate the power spectral density of the time varying signal. Then we have to apply the Fourier time frequency analysis techniques to improve the spectral results for time varying signals. And we have to explore the different methods for the analysis and the visualization of the time varying signals. Then finally, the wavelet analysis is done to estimate the spectral characteristics of the time varying signals. So let's see some of the examples. Okay, which is one of the good example given in my MATLAB. That's why I kept this. Uh, so this course example is identify the gearbox faults. Okay, the power spectrum works well for some spectrum analysis problem, like we already saw. But if our signal has certain characteristics such as time varying frequencies, then you can get the better results with other spectral analysis methods. For example, you will have this ball bearing, this outer race and inner race. Okay, the perfect gearbox would have no vibration signal, but there will be some interference of some noise. So this examples generate and analyzes vibration data for a gearbox whose shafts rotate at a fixed speeds. Okay, so you may wonder, like in some cases we are only using this power spectral analysis, but in some cases where it is completely modified with respect to this time, then we are also using this time varying frequency analysis with the other spectral analysis methods. So here we will see some time varying signals Okay, the spectral estimation methods like the Fourier transform. Why we are telling what is a spectral estimation methods? Why this Fourier transform? Because Fourier transform is actually the transform of the signal in the time domain to a frequency domain. Okay, because it is not simple a simple representation. When we write the simple representation of the time domain signal in terms of the harmonics of sine and cosine, then that is simple a Fourier series. Okay. But when we transform to a one domain to another domain, that is called transform. So whenever this transform word, so that's why either it can be Fourier transform, jet transform, Laplace transform, where it is applied to different types of signals. We will see that as well in the LTI system. If that is covered as a part of week 9 or 10, we will see that as well. So this Welch method are designed for the signal with a constant spectrum over time. So what is a constant spectrum? What is example of constant spectrum? Can anyone tell me what is example of constant spectrum? There are so many students joining my class. Raja used to answer. Anyone? Ishan, Ketana. We all saw this noise, right? Noise was what? Constant spectrum, right? Because the magnitude was n naught by 2. Okay. Okay, let it be. So, for example, the frequency of a single note on a keyboard is a constant for the if this single note in the sense single frequency. Okay, it will be constant for the single entire signal. So, constant frequency content. Suppose this is the constant frequency content, and the time it is varying, and you will have the power spectrum densities like this. Will we have the power spectrum, the spike at particular frequency, and it is going down. Okay, if you analyze a sequence of notes, the frequency content changes over time. So if you use the same methods for the signal with the constant frequency content, so you will lose the time information. So I'm trying to say is the frequency content changes over time. So in that case, we cannot use the same methods for the sequence with constant frequency content. Otherwise, you will lose the time information. There are some exercises, we will see that as well. Sorry, this is creating this time issue. Okay. So in this activity, we will see this we will observe this spectrum for the vibration signal of a gearbox. Okay, that we already saw. This generated signal simulates the vibration signal for about 5 minutes. The shaft for the gearbox rotates at a fixed speed. You have to import the two signals, a healthy signal from the gearbox and the faulty signal that will localize fault at the some point. To compare the frequency content of the monitor signal with the healthy signal, you have to first visualize the power spectrum of the healthy signal. So how can we visualize the power spectrum? P spectrum. P spectrum. And we have to first uh, give the name of the signal, which is a healthy gear. Anyone repeat with me? Healthy gear. And what is FS? Signal. FS. Okay. P spectrum. I think FS was already defined here. I should not get it here. We just have to power spectrum. So P spectrum. FS is already defined. I couldn't see. It is inbuilt. So here we can see the power spectrum and the FS is already defined in this task. Okay. Now to display the power spectrum of the monitor gear. Okay. So we have to display this We are very much handy with this displaying the power spectrum. Like we have done so much of things. Tab. We can have tab. It's S. In the year, the signal is already defined. Okay, signal is of this quality. Okay, next. Further, we can also observe the monitor signal contains an extra tone at 2K. So how 2K? Yeah, you can see here another spike is there. This indicates a fault in the signal from the gearbox. And if we use a normal power spectrum to find the spectrum of time varying signal, we will lose all the time information. As we can see, the normal time spectrum, if we find, we will use the time information. In the spectrum, you can't tell what time any of the frequencies occurred. The spectrogram can help you to find the fault occurred in the gearbox. So we had this time varying analysis two types. First one the spectrogram, another one was, anyone remember? So in spectrogram, we have to write the signal in the terms of sine and cosine. We'll see how. I think I can skip this, but still we have time so we can see this. You'll have that this time.
Signals from medical and automotive industries mostly exhibit time-varying frequency characteristics. In MATLAB, spectrogram and scaleogram
Yeah.
are two
So two methods are the time varying frequency analysis is a spectrogram and a scaleogram. So how these two refers, where it is a standard function for the time frequency visualizations.
standard functions for time frequency visualizations. A spectrogram is calculated using the short time Fourier transform.
So understand this. Spectrogram is calculated using a short time Fourier transform. So with different time intervals, you are calculating the Fourier transform. And the Fourier transform, the formula was summation from minus infinity to infinity xt e power minus j 2 pi ft dt. Okay. So what we are trying to do, we are multiplying this e power minus j 2 pi ft with respect to signal and we are summing it. Okay. We are just calculating the area and we are just calculating because e power minus j 2 pi ft has this two harmonics because that we can write as a sine theta plus j cos theta. Cos theta plus j sin theta. So sorry. Okay, because e power j theta is equals to cos theta plus j sin theta. So that is only giving the Fourier transform. I already explained you. If you have any doubt, you can just text me in the box. I think we have some notification. So let me check. You can just text. If you can just keep in chat box, I will see the chat box regularly. Okay.
The signal is divided into fixed overlapping segments, or windows.
Signal is divided into fixed overlapping segments of the windows.
A Fourier transform is then applied to each of these segments.
The segment is first divided into each overlapping windows. Okay. And the Fourier transform is applied over each overlapped.
In the spectrogram, the first segment's result creates one image row. The second segment creates the next row, and so on. The outcome of this process is a visual map where time is plotted against frequency, revealing
So we mean mm, make sure that we are just dividing into overlapping segments, not non-overlapping segments. It has some meaning. Why overlapping and why not overlap? Can anyone tell me? Because see, we are having the values in terms of 1 segment, 2 seconds, and 3 segment. And the time is only affecting here. Okay.
Signal's frequency content as it evolves. In a spectrogram, the choice of window, window length, overlap, and DFT points are crucial. For example, increasing the window length and overlap will make the closely spaced frequencies distinct.
If we increase the overlap length, okay, and window length, it will make the closely spaced frequencies distinguishable. How? Window length is in the sense is what window length you are taking as a samples per time, as per the time. And if we are increasing the overlap also, so the frequencies you can see as a distinguishable. How? Anyone?
Distinguishable and smooth the spectrum.
It will smooth the spectrum as well.
Not all signals fit neatly into the framework of a spectrogram. For example, an ECG signal has slow varying components and high frequency transients. Moreover, the ECG signals are not very sinusoidal in shape, which makes them less suited for spectrogram analysis. Wavelets best model ECG signals. Hence, the scaleogram provides more insight.
So wavelets are best for the ECG signal because that is not very much time varying as compared to the other signals that we have in practice.
Into the ECG analysis. You can notice the steady state oscillations near 30 Hz and 37 Hz, and the transient events denoting the heartbeats. The scaleogram is calculated using the continuous wavelet transform.
So yeah, uh, the spectrogram was calculated using short time Fourier transform, where the scaleogram is calculated using continuous wavelet transform.
The CWT compares the signal to compressed or stretched versions of a wavelet. Longer wavelets are used in regions of low frequency, and shorter wavelets in high frequency and rapidly changing areas. This adaptive windowing results in unequal segments of signals. The wavelet transform is calculated for each of these segments to get a scaleogram. The adaptability ensures that both high and low frequencies are captured. In summary, the spectrogram and scaleogram offer invaluable insights into time-varying frequency signals. You can choose between a spectrogram and a scaleogram depending on the signal's characteristics.
Just give me a second. Okay. Next module is Fourier time frequency analysis. So the spectrogram function we will see, the spectrogram function computes the short time Fourier transform, revealing of signals frequency spectrum over time in 2D image. Okay, so suppose the spectrogram function provides a lots of ways to customize the spectrogram. So spectrogram, the signal is there. Okay, the signal is input signal. Then window, the signal is divided into segments of the same length as the window vector. Number of overlap. Okay, the number of overlap points because we need to create in terms of number of overlap. The number of DFT points. Okay, and FFT. So you might also DFT and FFT uh doesn't vary much. This is same only. The FFT is the fast Fourier transform of DFT. The FS is a simple rate. So you can use the script to visualize how window length affects the spectrogram. In this example, there are two tones in the signal, one at 25 hertz and one at 26 hertz. So how you can see two tones? This is 25 and this is 26. Okay. But in the spectrogram, only one tone is visible. That's great. Try changing the window length until you can detect the both signals. So as we know, increasing the window length only, we can see this two tone. Let's see. Uh, can we see this two tone? Oh, yes. So 25 and 26, we can see this two tones, right? You can detect two frequency once you increase the window length, right? Correct. So this is because a large window length captures a large segment of the signal, which results in a high number of samples for the Fourier transform. Okay. As a result, the frequency resolution is good and the spectral peaks are narrow and well defined. So frequency resolution is good and spectral peaks are the narrow and well defined in the sense that in the script, the number of overlap and the number of DFT points are set to default values. So if you want to see the code used to create the plot, you can see this title. So there are certain types of windows. Okay, windowing helps mitigate the certain issues and artifacts associated with analyzing signals over their entire duration. They have few common types of windows in use in the signal processing. First, in the rectangular window, Kaiser window, and the Hamming window. Simplest form of window, it multiplies a signal by a rectangle, simple rectangle. A vector of ones of the appropriate length is used at the windows. A rectangular window has a constant amplitude within its interval, leading to sharp transition between 0 and 1. This characteristic makes it easy to implement and computationally efficient. The Kaiser window is a window controlled by the shape parameter denoted as a beta, where a larger beta value results in a narrow main lobe but increased side lobe suppression. Narrower main lobe but increased side lobe suppression. We can see this Kaiser window um, in practice. See, this is Kaiser window. Okay. So as this beta is what? Like we had this parameter. So beta is increasing, you have the narrower lobes. So this is what the Kaiser window looks like. The Hamming window tapers the signal smoothly at the edges. Sometimes we don't understand. We just have to type it here. We can see here. Okay, so this is Hamming. We can taper at the edges with some controlling parameters. Most windows can be created with functions that correspond to window name. For example, make a Hamming window. We can use this window. If you like to learn more, you can see this head spectrum analysis. So in this activity, you will compute the spectrogram for the vibration signal of the gearbox. The inputs to the spectrogram. How many students are still here? No chat. Okay. So you will see the inputs to the spectrogram function as spectrogram S window number of layer and you'll say you will use a rectangular window. Rectangular window function is a vector of ones. Okay, ones. It it will create a square matrix. The window will be a vector, so you will have the two inputs. How will describe the spectrum of monitor here? So so here we'll have this. First of all, we need to create the so rectangle one is nothing but default values for the DFT. So default values for the DFT simple no overlap. So I think 0. Okay. So like this we can create. Even though the gearbox signal varies over time, the spectrogram shows that the frequency do not change. Okay, so this is because of an incorrect choice of the window length. Okay, so the window is the same length as a signal. So isn't it divided before the spectrum is actually calculated? To see how the signal changes over time, use a smaller window. So display another spectrum, but this time use the default values for the window overlap and DFT values. So for default values, we have to just keep. So this is better than before. Another value you might want to change is the frequency axis. So you can swap the axis so that frequency on the y-axis and time on the x-axis. Display another spectrogram with default values. This time visualize the frequency on the y-axis. There's some error. What I did, I don't know. Top 3. Okay, simple shit. So what I did wrong is Unnecessary keeping this dash symbol. That was not required. Okay. So in the last plot, you can see how the signal was divided into 8 segments. See this last plot. 8 segments. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. The default values of the spectrogram are the Hamming window that divides the signal into 8 segments with the overlapping symbol, 50% overlap between the segments, either 256 or 2 power next power 2 length into DFT, whichever is larger. So we already saw the spectrogram analysis, which is different from the power spectrum analysis. The spectrogram in the live script uses a default setting for the spectrogram function, which divides the signal into each segments. In the first few segments and the last couple of seconds, the noise level is very low, around minus 120 dB. So after around 2 seconds, the noise level increases by a small amount, and there is also a presence of extra frequencies. This indicates that the gearbox fault occurs sometimes between 2 and 4 seconds, but not very precise. How you are seeing that? Because it is increasing only by a small amount, and there's also presence of extra frequencies. The spectrogram is actually fast to compute because only 8 spectra are calculated, but that also does also mean that the spectrogram has very blocky appearance. That's very true. We can often see from here that a blocky appearance is only leading to the confusion between getting the actual value to the illused value. Okay, that's why it is creating another blocky experience. In this activity, we will decrease the window size. Okay, let's decrease the window size. Once a well did happen window. The happen window, fine. So how to create, I was just getting that. Okay, that's true. Okay. Display the spectra, okay? Now, instead of default values, you'll keep this. That's great. So here we can see this more accurate, not a blocky appearance. So you can compare this with this blocky appearance, and this one is blocky appearance and this is non-blocky appearance. That is strange. You can see that the extra frequencies got added right at 3 seconds. Okay, the extra frequencies, okay. So that when the fault occurred in the gearbox. This is a block, right? This is not a block. quality experience. So I think we understood the spectrogram more. We'll just move to the week 8 questions, or else we will just finish this task, then we'll go to week 8 questions. Okay. The display spectrogram is useful if you want to visually inspect the plot. Okay. But if you want to go further, you can get the output on the spectrogram to get the spectrogram in a matrix. So change the spectrogram command to have 4 output arguments, such as S, F, T, and PS, in that order. Don't use semicolon, okay, at the end of the command so that you can see this result. So S, F, T, PS is equals to. So we can see these output arguments, okay? The matrices S and PS are of the same size. Now we will play with the S and the PS. For both matrices, time increases across the columns and the frequency increases across the rows. That's great. Frequency like this, time like this. Okay. Starting from the 0. The time row vector T labels the columns and the frequency column vector F labels the rows. How are S and PS different? Notice that the S is the complex and PS is the real. Okay. Whereas S is a short time Fourier transform. Okay. And the PS is the power spectrum. If you want to display the power spectrum at one instant, you should use the power spectrum PS. Let us save this power spectrum at first instant or first column of PS to variable name first slice. First column. How can you save the first column to P first slice? Rows and columns. Okay. So we want all rows, one column. So here we correctly did. Okay. No, first let's correct. Let's see the solution. First let's I took like this only. Oh, okay. Plot, I can directly plot. Okay. Why to plot this power spectrum always? So directly we can see the time domain. You will observe that the prominent frequency in this plot are of healthy signal. If you zoom in and add data tip, you will get 3 prominent frequencies. This is cranial input, then shaft frequency, then a gear shaft frequency, gear mesh frequency, and you can Add a data type from the View tab in the Tools scripts. Click on the plot where you want to add the data type. Okay, we can add this and we can see this. Okay, so I will just share my screen to discuss this is a week 8. Given that the signal sampled at W samples per second and is quantized in L level quantizer, the resulting digital signal has a rate of what is the answer? Anyone? So as we
Ma'am,
know
W
that,
log 12.
yeah, so W log 2L. Why? Because when we quantize, so we'll have the level as 2 power n. But when we do the quantization, okay, so suppose the quantization step size is V max minus VB divided by 2 power n. Okay, so this is named as W, okay, or 2 power n. Okay, and this is level. So level is 2 power n and n is log 2L, where we are having this step size, this W samples per second. So we have W, number of samples per second is W, and then the bit size is N. So it is asked like rate is given by W into N, where N is log 2L. That's why rate is W into log 2L. Okay. And speech is considered as a wide sensation for a period of 40 milliseconds. That is simple, the fundamental that we can have in the class. Why it is 40 milliseconds? Because wide sensation in the context of speech signal means that a statistical. We can see that given the variance of the random process is sigma x square and its innovation component is sigma v square, then its maximum processing gain, what is this is sigma x, this is sigma v, okay, and this is some LPC. So it is nothing but a sigma v squared is sigma x squared. Processing gain, I think, one sigma x squared by sigma v squared. Why it is x by y? Because in linear predictive coding, the goal is to model a given random process as a linear combination of the past symbols, samples, plus the innovation component. So you can see this processing gain. Some things you can actually do that. The Fourier series maps one period of a continuous periodic signal to a discrete frequency components. So I think second, and you always remember what is different between Fourier series and Fourier transform. This is not same. The only scientist is same. The Fourier series gives a representation of the time domain continuous signals in the form of discrete harmonics of the sine and cosine. So answer is second. And the fifth question is, Two complex valued signals xt and yt are called orthogonal when their inner product is 0. So inner product is xt, yt, dt minus infinity to infinity by t. So by actually when you have two signals like this, suppose so answer will be, and you'll have this y conjugate t. So answer will be first. The Fourier series maps on a basis with an uncountable coordinator, basis with the countable coordinator. It is very true because you have the signal from all the periodic signal are infinity in time domain, not constant or the band limit. So you are leaving. Okay. So basically, the Fourier series maps from uncountable basis to a countable, where because all the periodic signal Fourier series is only defined for the periodic signal, and all the periodic signals are uncountable, having the uncountable values. So we actually maps it a countable one to a Fourier series. The command eigenvalue gives the R sorted in this order. So this is eigenvalues in ascending values. So this is in MATLAB. We can see that as well. That is not a problem. We can use MATLAB to perform time frequency analysis of the signals. We already performed, right? Today we saw all those about the time frequency analysis with the spectrogram, the scaleogram. So very true. Okay, so this was the question from the week 8. And I hope you understood some part of some part and some analysis. And thank you so much for joining. So Amber, Deshant, Manisha, Parul, and Raja was continuing till here. So if you have any doubt, you can just let me know so that I can just have a discussion. So Amber, yeah, tell me
Excuse
please.
me, ma'am.
Yeah, yeah, yeah.
Ma'am, I checked, ma'am, last recording, ma'am, seventh one. So, ma'am, this assignment was, I think, discussed in that one, and ma'am, that time you missed week 7 that time. I
No, no,
noticed.
no. Oh, week 7 previous year assignment was not given anywhere. So that's why I couldn't discuss that. You want me to discuss week 7, right?
Yes, ma'am. Can you please, ma'am? Actually, no. This time, ma'am, in week 8, there was a question which was in actually week 7 assignment last year, ma'am. But in that answer was different, and in this one now, in the evaluation, answer is different given, ma'am. So
Okay,
actually, I
can you
need to,
please mail me that question?
ma'am. Actually, I think it is related to Lampel-Ziv encoding. I think you
Yeah,
may.
yeah, yeah. Okay, 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 okay. Okay, okay.
So is it Lampel-Ziv or it is sub-band? I'm not sure, ma'am, actually, because in last year it was given Lampel-Ziv, ma'am.
Okay, 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 okay. I think last week I couldn't cover this week 7 assignment. Okay. And this time also okay. Okay, so I will just check with that question. I will definitely take care in the next class. Okay,
Okay, ma'am.
I will check.
Ma'am, can you give me your mail ID, ma'am?
Yeah, yeah, sure. I'll give. I'm writing in the chat box. You can check the chat box, right?
Ma'am, actually, ma'am, I'm unable to chat. I think maybe I have joined as a guest, so I think so. I'm not
Oh,
able to
sure.
chat
Okay.
here.
So you can write this EE21
EE21
RESCH
RE
SCH
SCH
010
010
01010 again 10
010. Then, ma'am,
10
10
at the rate
at the rate
IIT
IIT
H
H
dot AC dot in.
dot AC dot in. Okay,
Yeah, yeah.
thank you, ma'am.
Yeah.
Thank you.
So I will check that question and then I will let you know in the next class. Okay.
Okay,
And
ma'am.
since
Okay, ma'am.
there are two TAs for this course, and that is Shwati. Shwati is also teaching, so you can check her lecture also. So since both of our lecture are same, so that's why I'm teaching in this perspective of this simulation.
Ma'am
Form.
Shivani Dhok, I think, ma'am.
Shivani, Shivani. So you can check her lecture also. It will be uploaded in the YouTube. I will also check. So that question that you are talking about, I'll let you
Ma'am,
know in the
actually,
next.
ma'am,
Mm,
ma'am, I
yeah.
attended that session, but ma'am, she told me that she can't discuss that one because that was in that current assignment. So she can't discuss that, ma'am. So,
Acha, okay. So maybe we can discuss in the next class next.
okay,
That okay, okay. Thank you so much, Amber. Yeah.